Hello everybody, and welcome to exercise 4 on page 56. This is a problem that's similar to exercise 3 in that they're giving us the matrix of a linear transformation and asking us to use that to find the value of the actual transformation at a point. Okay, so let's read this together. So they start us off with two bases, beta equals this and gamma equals this, and t is taking us from R3 to P2 of R. Okay, and again, they're giving us this matrix and asking us to use the matrix to help us to figure out what t of negative 1, 3, and negative 2 is. Okay, how do we do this? Well, first thing that would be good to remind ourselves of is what is the meaning of this matrix? Remember that a matrix of a transformation takes us from coordinates to coordinates. So one way that we could start this problem is to just calculate all of the coordinates that we can. Okay, maybe starting with the input. Okay, we'd like to substitute this tuple in, negative 1, 3, negative 2. So how about if we start by finding the coordinates of that tuple relative to this basis? Okay, we can do that. Okay, by just asking, how would we build that negative 1, 3, negative 2 as a linear combination of these three vectors? Okay, so what goes in those blanks? Okay, now you may be able to do this in your head. Okay, I can't quite do that. There's a few too many ones in here. So I'm gonna give those variable names. What we'd like to do is to figure out what A, B, and C are. This comes down to a system of equations. So if you wrote it out, it would look like negative 1, the first coordinate, has to look like A plus B. Okay, 3, the second coordinate, ends up being A plus C. Okay, and then negative 2, the third coordinate, is going to wind up being B plus C. Okay, I'm getting that just by kind of simplifying that equation up here. And I'm trusting that this is a type of a system that by now you can solve. You might be able to do that just using ordinary substitution elimination, or you could put it into a matrix, do row reduction. However you do it, though, what you should end up with is A equals 2, B equals negative 3, and C equals 1 as your solution. Okay, and so what that means then is that the coordinate vector of negative 1, 3, negative 2, relative to this basis beta, has to look like 2, negative 3, 1, those three coefficients that we just found. Okay, and I'm going to remind you of what this is that we just found. Okay, those are the beta coordinates of our input, negative 1, 3, negative 2. Okay, that's where we're at so far. Okay, it would also be good to know what the coordinates of the entire output are, t of negative 1, 3, negative 2. We can find that because remember, this matrix is the tool. That's how we get from coordinates for our input to coordinates for our output. So all we need to do to find the coordinates of the output would be to take our matrix, negative 1, 1, negative 2, 2, negative 3, negative 1, and 0, 3, 3, and just multiply it by the input coordinates that we just found, which look like 2, negative 3, 1. Okay, well, you would do that matrix multiplication. I'm going to trust that you can check me on that. And what you should come up with is this, negative 7, 12, and negative 6. And what we're looking at there are the gamma coordinates of the output, t of negative 1, 3, negative 2. How do we know that again? Well, it comes down again to the meaning of this matrix that we're looking at. This matrix takes us from beta coordinates to gamma coordinates, and that's exactly what we did. We started with beta coordinates here, and so what comes out has to be gamma coordinates. All right. Well, we've done a lot of calculations here, but where is all of this leading? Remember that what we're trying to figure out here is this, t of negative 1, 3, negative 2, and I think we can help ourselves to do that by drawing a picture at this point. Okay, so in a nutshell, what we're trying to do, what we're thinking of here is taking this vector -1, 3, -2, and substituting it into t, and we're going to get something out. We don't know what that something is yet. That's what the question is asking us. And what we've done in our work so far is to calculate coordinates of these things. So we discovered, whoops, not gamma, beta is that's our basis. We discovered that the coordinates of that vector, okay, our input vector look like this. There's that 2, 3, -1 again. And if we left multiply by the matrix that they gave us, we wound up with the coordinates -7, 12, and -6. Okay, and those were gamma coordinates for the output. Okay, so now the question is, how do we figure out what goes in that box there? Okay, well, the key is to remember what this calculation is telling us. -7, 12, and -6, those are the coordinates of the output that we're looking for. Okay, let me try that again. Okay, so even though this vector doesn't tell us directly what goes in the box, it tells us exactly how to build it. Okay, the -7, 12, and -6 are the coefficients on the basis gamma that will give us our output. So the last step here is just to notice that t of -1, 3, -2, we can get it by taking this times our first vector in gamma. Okay, let's see, what was gamma again? This basis. Okay, so I don't know if I can, sorry, I'm not going to be able to get this on the same screen, but -7 is going to get multiplied by this. Okay, that's our first piece. -7 times 1. Then we're going to take 12 times the second vector in gamma, which if we scroll up and sneak a peek is going to be 1 plus x. Okay, and then finally we'll take -6, and I'll let you look. That's the third vector in our basis gamma looked like 1 plus x squared. Okay, and if we can do that arithmetic, we have the answer that we're looking for. So let's see, -7 plus 12 plus 12x minus 6 minus 6x minus 6x squared. Okay, and I'll leave it to you to just double check my simplification. It looks to me like that's going to work out to be -1 plus 6x minus 6x squared. And there's our result.